So we discussed some unbounded operator theory. So I will tell you what, I will state the spectral theorem, and then we will see how to prove that. Okay? How we prove among ourselves. So for that, the first definition is, let H be a Hilbert space. Mostly we will deal with separable Hilbert space. Then a function, and you can take any omega, but we will take a subset of R, mostly subset of R or real line itself. Okay, so let omega script f be a measurable space. Omega is a set and script f is a sigma algebra. Be a measurable space. Then a function p from, so H be a Hilbert space and P of H is all projections. Okay. You take the collection of all projections on H, equivalently all subspaces of H, you call it as P of H. And P is a function from, it's a set function defined on the script F, the sigma algebra, to projection H. Is a spectral measure. I call it a spectral measure. Usually it is associated with an operator, bounded operator or unbounded operator. Is a spectral measure. Measure on omega. If, so these are sets, and for each set, it lands up in a projection. You get a projection corresponding to that. Okay. So P of whole set omega equal to the identity, and P of the empty set equal to 0, of course. And P of, so it has to be countably additive, it has to be finitely additive and countably additive. I directly write the countable additiveness. So this implies if there's finite, then it's finitely additive also. So this is En intersection En is empty if n not equal to m. Okay, they are mutually disjoint collection n equal to 1 to infinity equal to summation n equal to 1 to infinity. It is the same as the definition of a measure. But this sum is, as you know, that I already demonstrated sometime, when you are taking projection, you cannot take you cannot use the strong topology. You cannot take the norm topology. Okay. For example, if you take the sequence of subspaces, if you have a H, and if you have a sequence of subspaces Mn containing H, and Mn subspaces increasing to H, that is union of Mn equal to, I mean, Mn is contained in mm for m greater than n, union of m equal to H, then P, the projection onto Mn, which will converge to 1 in strong topology, not in norm topology. It cannot converge in norm topology because 1 minus Pm is also a projection. So they will have norm 1. So it cannot happen. So we have to use strong topology. If you apply that sequence on any vector, then it will converge. Okay? So this is in strong topology. So whenever you say about infinite sequence, you have to, in series or something, you have to say the topology, infinite summation. It is in strong topology. So this is what is a spectral measure, just instead of a measure. So you can similarly define measure taking values in real line. Usually measure takes values in 0 infinity, but it can take values in R, but it can take values. The point is, 0 infinity measure can be infinite, but here it will take the value. I mean, it's like a probability measure. P of the whole set omega is 1. Okay. For instance, so if you have a measure like this, then you can get a correspondingly a probability measure. So let us take U in H. Okay. And you can, I mean, you will get a finite measure. If norm U is 1, then it will be a probability measure. U in H, then you can define PUU. Okay, PUU is a measure from script F to 0 infinity, which is defined by PUU of, I mean, I write 2U because you can take a U and V and define this. Or you can just take PU or something. Okay, I mean, I am used to writing PUU. You can take PUV, then we will get a complex measure. But since we haven't discussed complex measure, I am not going to state that. Positive measures are enough for our purpose. Okay, of any E is equal to P of E. I mean, given a spectral measure, P of E, U. That's all. As you can see that P of E is linear. I mean, you can put P of E anywhere you want. You can put in the second coordinate or first coordinate. Usually, it should be in the second coordinate. I mean, second place. Okay. The reason is that is where it is linear. But since P is projection, you can take it this way or that way. Doesn't. Okay. So maybe I'll write properly. U, P of E, U. So which is also equal to P of E. You can take P of E equal to P of E square. So this is just U, P of E, U, which is equal to norm P of E, U square, which is certainly greater than 0. Okay, this is greater than 0. And PU of whole of omega is 1. That is P of omega is 1. So if norm U, no, P of P U of omega equal to norm U square. Okay. So it's a positive finite measure. This norm U square is finite. So PUU is a finite measure. So if you have a spectral measure, and if you fix a vector U, using this prescription, we can always get a finite measure. Okay. And it will be a probability measure if U has norm 1. Okay. So the this collection of PU will determine that spectral measure. Okay, that's a different thing. We will come to that later. So this is what is called a spectral measure. So why do we study the spectral measure? Because any operator, any self-adjoint or normal operator can be written in terms of spectral measure. Okay. So if f is a simple function, that is f is equal to summation some lambda I 1 ei. Okay. Then you can define integral f with respect to the dp, okay, over omega is equal to summation lambda I p of a. This is a finite summation. So this will be an operator. Okay, this will be an operator with the eigenvalues lambda and eigenprojection p of a for simple functions. Okay. Okay. Now, if f is a bounded function, then there exist, Fn simple functions such that Fn converges to F uniformly. Bounded function or L infinity function will also do. Okay. Uniformly, you can approximate any bounded function, any infinity function uniformly. This is proved in the measure theory class. Let us not go into that. Then you can prove that, then it is a fact. You can actually prove, norm of, you can define norm of integral Fn. Maybe you'll try to prove it. dp minus integral Fm dp. Okay. So what is that? Summation lambda I p of. So this will have a summation. This will be less than or equal to, this will be less than or equal to the norm of Fn minus Fm. Which norm? The uniform norm. Okay. The infinity norm. Because dp is 1. So it will be, you can prove that this will be less than or equal to 0, which goes to 0. That's clear, no? You can write Fn minus Fm in the same integral. And the infinity norm, you can always take the supremum, infinity norm outside of Fm. You can do it for any integral, provided the total measure is finite. But here you have put a norm. If you write it as an operator, summation lambda a or whatever, all this p of a will have less than or equal to 1. Right? You write it in terms of that. This is check. It's clear, no? You take the definition. This is equal to summation lambda I p of a. Okay, keep it like that. And the supremum norm of Fn minus Fm is going to do. Fn minus Fm is also a simple function. Supremum norm is supremum of those lambda I minus mu I, whatever. That will come out. And since this converges, it will go to 0. P of EI, all those have norm 1, operator norm 1. Okay, so because of the operator norm 1, so you can take it out, this goes to 0. This implies this, whatever we have, that is an operator. Integral f and dp is an operator. Linear combination of projections. They are linear combination of projections. It's an operator. See, that's how we have written. We have written here. Integral f dp equal to summation p of ei are projections. This is almost like a matrix theory, but for simple function, but not for a general operator. Okay? Integral f dp equal to summation lambda I p of ei. Each p of ei is a projection. You take linear combination of those projections. That gives an operator, some arbitrary operator. Okay. Now we have an operators. So each integral fn is an operator, integral fm is an operator. That difference tn minus tm, whatever, that goes to 0. So it's a Banach space, so it should converge. B of h is a Banach space. So there exists a limit such that integral fn dp converges. And you call that limit as integral f dp for any bounded function f. F is any bounded function, then you. Okay. This limit, you can prove that this limit does not depend on. We will come back to this again, so I'm not proving it. This limit does not depend on the choice of simple function. I mean, which you always have to prove for well-definedness. So you can, for any bounded function, so if you have a spectral measure, for any bounded measure of function, you can write b of dp over omega. And you get an operator, which is an operator. In particular, if some set, so you have a sigma contained in R, which is compact. Okay, it's compact. That means it's closed and bounded. That's how any spectrum of any operator will be, normal operator will be compact. Okay, then the identity function x going to x, t going to t. That function is bounded because it's sigma is compact. Okay, then you can define this integral t, f of t equal to t, dp over sigma. This will give an operator t. Okay. Spectral theorem says the converse. If t is a normal operator, normal or self-adjoint, let us say self-adjoint, because we want our sigma to contain in R. Otherwise, you have to take C. Okay. T is self-adjoint, adjoint operator, and whatever it means, I will define what is this. Sigma T is a spectrum. I mean, sigma T is equal to all those lambda such that T minus lambda I is not invertible. This definition is not same as the finite dimensional definition. Finite dimensional T minus lambda is not invertible means T minus lambda is not 1, 1. Is equivalent to that in finite dimension. That means there exists a vector such that T minus lambda is equal to 0. That means T is equal to lambda z. So if it is not invertible in finite dimension, means lambda is an eigenvalue. There exists an eigenvector. Eigenvector means T is equal to lambda z. This is what is eigenvector. Not invertible means this statement. But here it may not be onto also, which is also possible. Okay, so it's not true that in infinite dimensional, T minus lambda I is not invertible, does not mean lambda is an eigenvalue. Okay, you have to be careful. It's not an eigenvalue. Okay. So this is so, but you have to take all those things. T minus lambda I is not invertible. Then sigma T will be a compact set. Then, sorry, I'm just making statements, not giving proof, because we have to do it later. Okay. Then sigma T contained in R. So for self-adjoint operator, spectrum will be contained in R. Okay, is compact. Okay, and you can associate a spectral projection, and there exists a spectral projection. There exists a spectral projection. Spectral measure. Sorry, didn't I say spectral measure? Spectral measure. P from Borel sigma algebra of G of sigma of T to P of H such that this T is equal to the function T over sigma T d. By this integral, whatever we do, we write. If you evaluate the integral for this function T, then you will get that T. But you can take any continuous function and measurable function or sigma of T. I mean, not measurable function.
So there is bounded operators on the right.
Which is?
It's from Weyl sigma algebra to bounded operators.
Yeah, projections. If P is a bounded operators, you can take projections. I mean, it's not just bounded operators, it's on projections, right? Projections. Yeah. I mean, it lands in projection. P is a spectral projections. So then you can write this integral. It will be. In fact, if you don't like the spectral measure, it just implies that T xi eta, T xi xi is equal to integral over sigma T, T, or I mean, T, D, P, you have this measure, no, xi xi, which is a positive measure, finite measure. So it is just the direct, that integral, basically. Here, there's no confusion about it. You don't even need to know what is spectral measure or something, spectral integration or something. This is just the ordinary integral of the function T going to T. You just integrate it with dp xi xi. I mean, if you have a spectral measure, you get a finite measure. If you integrate with respect to that finite measure, the T, you get that T xi xi.
T is some function.
T is the small T going to T, identity function. T going to T function. I mean, you are integrating T. See, is it okay if I write T there?
So, but aren't we integrating functions from omega to R?
Here, functions from omega to R, correct.
So, omega is R itself.
Yeah, I have taken omega to be sigma T, which is contained in R. Which is contained in R. Yeah. Here I'm taking sigma T. I mean, it's contained in R. Oh, there also it should make sense. When I said omega, there you should have asked this question. There, yeah, it should be contained in, correct. Correct. Yeah, there it should be a bounded function. Right. So this is what is spectral theorem is. Okay. Now, if T is an unbounded operator, okay, then you can talk about the same sigma T. You can define the same way, which is just, I mean, for that it has to be a bounded operator. For it to define x minus lambda I is a invertible bounded operator. Supposed to, yeah. Yeah. Now let's talk about spectral projection. So suppose P from R, the whole of R. Okay. It need not be R, it can be a unbounded subset. It need not be a bounded subset. That's what I'm saying. Rho P from R to P of H be a spectral measure. Some spectral measure. Okay. Then, so let F be any measurable function. R to C, let's say, be any measurable function. Okay. Then you define df equal to all those xi in H such that integral mod f square dp, you can write this, yeah, dp xi xi. You have this measure xi xi is finite. Okay, this is df. Okay. So on this we can integrate. When D
From R to C,
F is any R to C, be any measurable function. Okay, measurable I always write like that. Measurable function. Then DF be this subspace, okay, such that for all P is I. I mean, you can see that P is I is a xi going to P is I is linear in xi. You can take the, so this will be a subspace. Okay. Okay. So what I will do now, if you have any, now there exists bounded function. Now f is fn is bound. If fn is bounded, if f is bounded, I mean P is a finite measure on R. So if f is bounded, then this it's L2 integrable for all f. I mean for any bounded function for a finite measure is L2 integrable, square integrable. Okay. So then df is equal to whole of h. Okay. So you can define the same way. So integral f dp makes sense if f is bounded. Okay. Now if f is unbounded, there exists bounded functions fn converge to f, I mean pointwise or something. Almost everywhere. I mean usually almost everywhere is enough, pointwise. Okay. And it's a fact. And fact. I'm not proving it. Fact that integral fn dp will converge. Will converge. I mean, which is some integral dp acting on any xi converges. This is what we should prove for spectral theorem. Converges for all xi in domain of f, df. Okay. Take that limit. Okay. So define integral. So fn or bounded function. I mean, if you have any unbounded function, you have bounded function. You can truncate it and then you get a bounded function which will converge. You can truncate it by some n, I mean, bound by n. So you do wherever on the set where it, more than n or something, you just make it 0. Okay, so you will get a, you can truncate it. So then those bounded functions, this integral makes sense. It's a fact that that integral acting on the xi for all those xi in the L2 into df, okay, converges. Okay, so you can define integral f dp xi is equal to that limit of integral fn dp xi. Okay. Okay, so you call this, so okay, the domain of this function, this is an unbounded operator now, dp is equal to df. Okay. Domain of that fdp is a df and it's an unbounded operator. You get an unbounded operator. So spectral theorem says if T is self-adjoint, unbounded and self-adjoint. I will not write, just write self-adjoint. It can be unbounded or bounded. Then the domain will change. Okay. Self-adjoint. Then there exists a spectral measure on R, maybe a subset. I mean, but doesn't, I mean, the subset is spectrum. Okay. On R, such that T is equal to integral over T R, but you can make it 0. I mean, you can make the, on the spectrum, the support is in the spectrum, outside you can make it 0, T dp. This is an unbounded operator. I mean, there exists a spectral measure. Then this T, when the set is unbounded, this T going to T, this identity function is unbounded. Okay. So then you can define this T equal to dTp. This is spectral theorem. So this is what we want to prove for self-adjoint operator. Okay. So it will take it's a lot of work. Right? As you can see, even for compact operator, we have to work a little bit to prove spectral theorem, which I will prove in the Ghana one anyway. Okay. So this is something more. Okay. Now, why do I need this? This is because I want to prove the following theorem. I mean, I'm going to use this theorem. That is why I'm stating in this class, okay, which is due to Stone's. This is called Stone's theorem. Stone's theorem. The theorem is the following. So, see, if you have a unitary operator, which is a normal operator, okay, then it will look like e power ix for some self-adjoint operator x. Okay. Or let's say the following. If let P be a spectral measure, P from R to P of H, spectral measure. Then you can define ut to be, if you have a bounded function, I mean, the spectral measure need not be, it can be defined on whole of R, but if you have a bounded function, you get bounded operator. So this is a bounded function of e over it. Yeah, t is outside and its integral is x minus itx dpx, okay, over R. So you can do that integration and you get a ut. Okay. I mean, actually, we need the statement of spectral theorem. But since it's a math class, you have to prove. If it's a physics class, you can just state it and go. Okay. We don't need. Okay. So ut equal to e power itx is the spectral measure. I mean, this gives a unitary because they have norm one. That function, mod one. Okay. This will be unitary. If you have a function, I mean, it can be proven that if you have a function taking values in the circle, then you will get a unitary. Okay. If a function is positive, then the operator is positive. Okay. I mean, you can prove all that. That is clear. So ut star will be the bar inside. And these integrals are multiplicative in the sense that if you have some function, it is true that f dp times integral g dp will be f g dp. I mean, this integral is a homomorphism on this function space. It is not usually the case, but this kind of things are like that. Okay. So because of that, if you want to take the bar, if you take the bar, projections are self-adjoint. If you want to take the star, you have to take the bar inside the function. Okay. I mean, if you have the integral of f dp star will be just equal to integral of f bar dp. Okay. So it will become the integral. So by the multiplication statement, a multiplication property of the integral, it will follow that e power a, I mean, it will be, you will get 1 inside and it will be 1. If you integrate 1 with the spectral measure, you get 1. 1 is a function, that one is the identity operator. So this is a unitary, group of unitaries. This with T and R is a unitary group. And let x is equal to integral T dp, okay, which is an unbounded operator, okay, which is a self-adjoint operator. Because T is in the R, if you want to take the bar, you have to take the bar inside, and T bar is T. Okay, self-adjoint operator. Okay. Then the domain of then it is true that ut equal to e power minus I tx. Whatever it means. You can define it through functional calculus, or you can define it as a e power itx can be directly defined on the space, which is just equal to summation minus itx power n by n factorial, n equal to 1 to infinity. This sum converges in norm. Okay, you can take it this way, or you can, there is something called functional calculus, using that you can define. Okay, you can define it anyway. Or if x is an unbounded operator, that has a spectral measure. Okay, see, if you have t is an unbounded operator, that has a spectral corresponding spectral measure, and t will look like this, right? Okay, then f of t you can define to be integral f of lambda dp. Okay, this is one way you can define f of t. So e power itx can be defined through this, which is what exactly that says. Okay, spectral theorem. Conversely, if you have any ut, a unitary group, then there exists a spectral measure and there exists a unbounded operator defined through the spectral measure, such that ut equal to e power itx. I mean, I don't have to. So conversely, same thing. Conversely, if ut, any ut, t in R. I forgot to write, sorry, I forgot to say something more. And the domain of t can be defined through that. Then the domain of t is exactly equal to this. Domain of t equal to all those xi in h such that ut xi minus xi divided by t. This derivative exists. Limit t going to 0 exists. This limit exists. The domain is precisely that. And this t is defined by the derivative. Okay, this is what the Stone's theorem. The statement is this. I mean, utx, there is not much statement, because it's a spectral theorem. That is just the property of the spectral measure. Ut equal to e power itx. That is just the property of the spectral measure. But the domain of t is exactly equal to this. Conversely, if some ut is given, then you can define conversely, if ut equal to t in R, okay, and then you can define a domain, then you can define just d equal to all those xi such that 2t xi minus xi divided by t, limit t going to 0 exists. Okay. Okay. And define t xi equal to that limit. Okay. That limit of t going to, that limit exists, so you can just define it. Okay. Then t is a unbounded operator on the domain t, possibly bounded also sometime. Okay. So then if you define the t like that, then it is true that ut equal to e power I. Oh, I forgot. There has to be a minus I sign somewhere. It's not precisely that. You have to multiply. Yeah, here in this you need a minus sign. What is the sign? What is it? So if you take the derivative, you will get minus ix. You have to multiply by I to get x, right? So I times this. I times this. Okay. Ut is equal to, so t is equal to I times this, then e power itx. For some reason, itx is there because we want x to be self-adjoint. Otherwise, it will be, if you just write tx, then that will not be that will be as an anti-Hermitian, whatever. Okay. Skew Hermitian. Okay. It will not be a self-adjoint operator. X star will be equal to minus x. Okay, it will have that property. So we want a self-adjoint operator, so you have to write it as x e power minus itx. Okay, so in the limit we have to write an I. That's right. No, if you differentiate it, you get minus ix. If you multiply by I, you get 1. Okay, so it's okay. So this is the statement we want to use. If you have any unitary group, then you can take the vectors where it is differentiable. Okay, and just define t equal to this, then ut equal to e power itx. That x is a self-adjoint operator. Sorry, this is t. Sorry, I have written x. This is t. Okay. then T equal to T star. See, this T equal to T star is a strong statement. T equal to T star says this D is already densely defined. So you have a star. See, that is what we, in the last class, if you remember, if you have a densely defined operator, then you can define T star. Okay. So then that T star has a star. T star is densely defined if and only if this is closable. So T star star you can define. So T star should be equal to T. Okay. That means both the T and T star are densely defined and T is a closed operator. T equal to T star is a closed operator. Okay. So there are all these statements are there. When I say T equal to T star, it is not just the operator matches. I mean, whatever the prescription, the domain also matches. Then only we, I mean, it is precisely the statement. Graphs are same. Okay. So, okay. So what is next? Okay. Okay, now we want to apply this to our whatever we are doing. So what we are doing, we are doing. So we have symmetric Fock space. Okay, H be a Hilbert space. Then this is a symmetric Fock space. And then for xi in H or U in H, whatever U in H maybe, we can define, we define WU. We define WU acting on E of V equal to E power minus norm U square by 2 UV E of U plus V is unitary. This is the Weyl operator, which is defined on the exponential vector, is a unitary. Okay, extends to a unitary operator. Okay, and we know that this W of TU, T in R, W of TU, T in R, is a one parameter group of unitary. Is a group. Okay, is a group of unitaries. Okay. Okay. So it has a generator, stone generator. So there exists a self-adjoint, unbounded self-adjoint operator. We have proved that this is strongly continuous also, right? UN converges to U, then W of UN converges to W of U strongly. We proved that, right? See, exponential vectors are continuous. Okay. So WU is strongly continuous, right? UN converges to U. W of UN will be you will have some functions, exponential functions times this, and that is strongly continuous, right? So it's a strongly continuous group. I mean, the reason is in Stone's theorem, we need strong continuity. I forgot to say. Then only that is true. Okay. So I didn't say. I just generally defined, but we need strong continuity. I forgot to say. If the unitary group we consider the Stone's theorem, whatever the Stone's theorem. If it is norm-continuous, then the generator will be bounded. Okay. If it is just strong continuous, not norm-continuous, but just strong continuous, then the generator will be unbounded. It is bounded if and only if the unitary group is norm-bounded. Okay. So we have to prove all those three theorems. Okay. Then this is a strongly continuous unitary group. You remember W of T, you know? So this is the Weyl operator, unitary group. So there exists a self-adjoint operator, P of U. Corresponding to this U, you get this P of U such that W of TU equal to e power minus I T P of U. So we have got a new operator, P of U, which is an unbounded operator, which has the, which has a dense domain. Okay. So now we want to study the property. So here, from here onwards, I will prove few things. Proposition. So 6:30 I started. So 7:45 I should stop now. The proposition. The first, so there is something called a core, which I didn't say, but I will say what is a core. See, if you have a self-adjoint operator, if T is a self-adjoint operator, T is this definition. You take definition. T is self-adjoint with domain D of T. Okay. T naught is an operator contained in T. Okay. Of course, that means domain of T, that is domain of T naught is contained in domain of T. And the restriction T restricted to D of T naught is equal to T naught. That's what it means. Okay. And if the graph T naught closure is equal to T, if T naught closure is equal to, you don't even need to write. I'm just saying that if you have a, I should have said in a different way. T is a self-adjoint operator with the domain of T, and let some subspace. A subspace D naught, say, contained in D of T is a core for T if the graph of T naught closure, or we don't need to, we have already defined closure already without by using graph. If T naught closure is equal to T, where T naught equal to T restricted to D naught. You have a subspace of the domain. You restrict your T operator to D naught, and if you take the closure of the graph of T naught is equal to T itself, T is a closed operator. Self-adjoint means it's closed. T equal to T star. T star is always closed. So self-adjoint means closed. Okay. So T naught. So this is what is called a core. Okay. So the fact is, it's a long proof which involves all this messy calculation using probability and other thing. That the exponential domain, you take the exponential vector, take the span of that, just span. Okay. That is a core for this P of U. Okay. So I can even go through the idea, but final, see the book. So this is the proposition. I will not prove the second property. First property is exponential domain is contained in P of U, where E is equal to span of exponential vectors. Okay. So here I should use V as E of V. E of V, V in H. You take all exponential vectors, take the span, which is a vector space, dense, which is a dense subspace, which we have proved. So that is in the domain of, that is in the domain. That is in the domain of P of U. Okay. That is number one. Number two, E is a core for P of U, for all U, of course. Okay. Okay. Is a core for that. In fact, I mean, maybe I will repeat again. E is contained in, okay, so I haven't defined the product of unbounded operator. So I will define it now. I'm sorry, I'm defining it now. If you have S and T are unbounded operator, this is definition. S and T are unbounded. Unbounded. Then the domain of ST, you can define it to be like this. You can similarly define some also will come. Wherever it is defined, that's all. Which is equal to domain of T intersection, domain of T, intersection T inverse. T inverse domain of S. Okay. So that you apply T, it should land up in the domain of S. That's all. Then you can define it, right? Just the composition. So this is the composition of unbounded operator. But they have to be dense and the other property has to satisfy. I mean, if it satisfies, then it's a nice operator. Okay. This is a very natural definition. Similarly, domain of S plus T is equal to domain of S intersection domain of T. Okay. Where you can take the sum. So sum and product. T inverse of domain of S. So that T of Xi should land up in domain of S so that you can apply ST. That's all. There's nothing else. Okay, this is how we define product. This is how we define sum and all that. Okay. So this is the definition. Now the third thing is E is contained in domain of P of U1 up to P of UN for U1 up to UN in H. You can take the product and all those product. So this just means that you can take the product and then the exponential domain is contained in all those domain of that. Okay, it satisfies the property. This is the third one. Then the fourth one is you can take the commutator. I mean PU, PV. Acting on exponential vector EW is equal to 2y imaginary part of inner product of U and V times E of W. Is that okay? Yeah. This you can guess from the Weyl commutation relation. This is clear. So I will go one by one. Let's see what we can prove. So proof 1. So what is domain of P of U? Domain of P of U is all those things where d by dt, W of tu, xi exists. All those psi such that this exists. Okay. This derivative exists at t equal to 0. I mean, if the derivative exists as t equal to 0, it will exist everywhere. See, if we have ut, if you have ut, xi minus xi, t exists. Suppose this limit exists. Okay. Then you can apply ut naught. Since this is a continuous function, you can take this ut naught here and ut naught here. Okay. Then the derivative will exist for ut naught for everything. Right. I'm just saying this. D by dt of ut, okay, at t equal to t naught is nothing but ut naught of dut by dt at t equal to 0. Because you just take, I mean, it's like this. This derivative at 0 is ut xi minus xi divided by t, this limit, t going to 0. Now you apply ut naught. Since it is continuous, you can take it inside the limits. Okay, then you will get ut naught. And ut naught is ut plus t naught because it's a group minus ut naught, which is equal to limit ut plus t naught minus ut naught xi divided by t, limit t going to 0, which is precisely d ut naught dut by dt at t equal to t naught. Okay, I'll erase all this, but this is all clear, I think. Okay, so why am I saying all these things? Why did I say all that? I said that if the derivative at 0 exists, it exists for all t. Okay, it exists everywhere. Ut is differentiable everywhere. For that xi, I mean, acting on xi. It's not, the derivative is not, I mean, derivative is a limit. So it has to exist in some topology. And that topology is strong topology. That's what this says. Not strong topology. That depends on some particular xi, acting on that xi. For a bounded operator, it will be everywhere. So that's really the strong topology. For a bounded operator, when ut is non-continuous, this derivative will exist everywhere and it will become a bounded operator. Okay. Because see, if you have a closed operator defined on H, whole of Hilbert space, it will be a bounded operator. Okay. That's what the closed gap theorem I talked about. Okay. So because, and don't worry if you miss something, because when we do all this P of U, all these things, it will be very easy. I mean, we just need the facts to do this. Okay. In the next course also, next course will be easier than this course. So we will not do spectral theorem and all. We will only assume spectral theorem and do that. We will only need the statement. Okay. So we will be doing more of finite dimensional probability and other things. Okay. I mean, in case you are attending, I'm not compelling you. So, okay. So domain of PU equal to this. Now I want to prove that, to prove exponential, I mean, the exponential domain is contained in that. I have to prove, I mean, the linear combination will of course will be there. So I have to only prove that at E of U, the derivative exists. Okay. But that is clear. Now, W of TU, let us just write what it is. W of TU acting on E of U. So I will do this calculation so that it will be useful everywhere. Okay. Let's do this calculation clearly. You take this W of, you fix a U in H, then consider this W of TU acting on E of U. Is equal to e power norm t square norm u square by 2 minus t times u v, okay, and e of u plus tu. Okay, this is the definition. Just I have written the definition on the exponential vectors. Now you know the product rule will follow here. Okay. See, if you have a derivative here, it's a scalar function. Here we have first I have a scalar function, which is an exponential function. Then I have something. Okay. So to prove that this is the differentiable, I have to prove that I mean the other, see, the product rule is, I mean, if you have you can multiply a vector by a scalar, then the same product, I mean, if you have some function, f is a function from somewhere, from R to H, okay, and which look like some f of t times xi of t. Xi is a vector and f is a function. Then you can, then f prime, sorry, g of t or something, f prime equal to g prime t xi at 0. I mean, g prime t at 0 times f of 0. You have to apply the product rule of the derivative, which will work here. Okay, so let me write it. Tell me.
E of U plus TU.
T equal to 0 equal to this derivative of this function, which will be just norm use at t equal to 0 means, which is just 2t minus 2t times e power norm u square t square minus t square u square by 2, okay, times that other functions. Maybe I will write the whole thing. if you take the derivative, this is going to be, this is equal to dw2, I mean, acting on EU, of course. EU equal to minus 2t norm u square by 2, okay, minus uv, okay, this function times at t equal to 0, of course. So at t equal to 0, so that the first thing will become 0. Then whatever we have here, that whatever we have to evaluate at t equal to 0. Okay. Plus this function e, whatever we have here, you have to evaluate at t equal to 0. That will become 0, 1, right? So then this derivative, the second derivative, I'm just using the product rule, which will, if you apply the limit, same how the product rule is proved in calculus, you do the same thing, it will be proved here also. Okay. How do you prove product rule? I mean, how do you directly, I mean, you can write it down, right? I mean, how do you prove? I mean, yeah, the same proof will work. Okay, whatever the proof, the same proof will work. D by dt, E of u plus tv, t, so v plus tu. Here it is u, v. I am confused with u and v. This is v. So this will be v. This will be, so E of v plus tu. Tu, d by dt at t equal to 0. At t equal to 0, right? So I only need to process other functions, the exponential function, nice functions. Okay, I mean, if you, so what we will get is the following, we get minus uv, okay, times E of u, okay, plus d by minus uv, no, minus uv, right, minus uv, plus d by dt, E of v plus tu at t equal to 0. This is what we get. I have to only verify that this function, so it's enough to prove this function t going to e plus v plus tu is the differential. That's what I have to prove. We can in fact compute the derivative. See, what is that? E power e exponential vector, not e power. What's happening? Oh, loose. Now E of v plus tu. What is that? Which is summation n equal to 0 to infinity. Okay. V plus tu power n, tensor n, right? That is how it is defined. Exponential vector is defined. Okay. Okay. Now you want to derivative. So you have to, at t equal to 0, you have to take e power minus t by t. Okay. Minus summation n equal to 0 to infinity v power v10 tu. So I'm sorry, did I mix u and v? Which one is v? Oh, I am acting on v. Okay, doesn't matter. Okay, by square root of n factorial. Okay. Now, if you expand this, this is like a power expansion only. V plus tu tensor n is going to be tensor n plus tu tensor. I mean, it will have all the symmetric things also. Okay, but if you subtract the v tensor n, v tensor will go, and we will have a t power n there. Okay, unless, I mean, yeah, and only for the first term t. I mean, only the t, this will have a t power n, no? T, so when you have the tensor t u power r times v power r, v power n minus g power s, v power n minus r minus s, something like that. Okay, there it will be there when you just, I mean, this v tensor n, the first v tensor, in the first term will be v tensor n. That will cancel with this v tensor n. The next term will be, for example, v tensor n minus 1. Tensor tu. And you will have a tu tensor v tensor n minus 1 also somewhere. Okay. So there, if you divide it by t, so you have to divide it by t. I am saying what you will get is tensor n equal to 0 to infinity, you have in the nth term, so let us say xi n, where xi n is equal to xi n equal to the symmetric, you know, the symmetric, maybe we'll write it. So n is equal to summation r is equal to 0 or is equal to 1, 1. You should know at least 1. 1 to 1 to n. Okay? V power r tensor u tensor p power n minus n minus 1 minus r minus 1 n minus r plus. This is what you will get the answer. If we take the limit also, sorry, we'll take the limit. You can take the limit in each and every term. Take the limit inside. Okay, since it is nice. So then this is what you get. Is that clear? Unless you say expand it, you'll get it. If you expand V, see if you expand V plus TU power n, you get V tensor n plus V tensor n minus 1 tensor TU. But at the same time, you will get this also. TU tensor, oh, TU tensor V tensor n minus 1 also. Okay. Plus other terms where T power T, higher terms of T will occur. Okay. So,
Divide by root n.
yeah. And not just that, you will get, yeah, you will get TU everywhere. Something like T, yeah, you have to divide by root n to n power also, but there will be, that will all go away. Yeah, you have to divide it by n. You have to divide it by that. You will have something like this also. V tensor, TU tensor, P power n minus 2. You will have something like this. Okay. And also you will have V square and the symmetric thing also. Okay. So that is what I have written here. And when you divide it by T, the T will go away. And when you T converges to 0, only this term will remain. All the other thing will go to 0. Okay. So xi n, and you have a xi n power n factorial, I think. Xi n by square root of. There will be a square root or not? There will be a square root of n. Correct. So that will be square. That's it. So I have computed the derivative explicitly. Okay. So this implies there is contained in domain of P of U. So the core, so this is the first statement. Okay. First statement is the domain is contained in domain of P of U. Okay, maybe I will take the class tomorrow. I have to go somewhere, but since I have many, I will come back. I will take the class tomorrow. Okay, 5:30 is fine. 5 o'clock is fine. If I'm delayed, I will call him. I have your number, so I will call him. Okay, I will call him and tell him. I'm going somewhere, but I mean, I will continue this. I will finish this Fox space theory, and then we'll start spectral theorem from the next week. Okay, so the core, I will just tell you what is needed to prove and what he is doing. What does it mean by a core? Core means you have a subdomain, you have a domain for an operator, you have a subdomain, and if you restrict that operator to subdomain, and then if you take the closure means you are taking the graph, not here. I mean, these are both are dense subspaces. If you take the closure, you will get H. So you are not taking the closure in the Hilbert space. Okay, you are taking the closure in the graph, in the direction of H direction H. Okay, so there you are taking the closure, and the closure of this restriction should be there. Okay, so that is, see, one thing I want to mention is you have this P of U given a W, given, you have Weyl operators. Using that, you got this P of U. Okay, this P of U, this domain of P of U is not determined yet. All operators. This is just an abstract statement. You have to list. You have to determine whether something is in the domain or not by some property. You have to list it down by some property. Okay, that is not known. It's an open problem, as far as I know. So I had some ideas to work on it, but I couldn't succeed. This was 10 years back. 2008-9, I was looking at it. Then I stopped looking at it. Okay, so that this domain is this domain of P of U complete. It's not completely known. So we work on these exponential vectors, which are a core for that. Okay, so now we want to prove that exponential vector is a core. That is, you take a chi. Okay, chi is a vector. Chi is in H such that you take chi is in the domain of that. Chi is in the, you want to say that yeah. So that is the closure. Chi is in the domain of P of U. Okay. Then you have to take this chi, P of U chi, which is in H direction H, right? And you assume that this is orthogonal to all those vectors. E of U, P of E of V, P of U, E of V. Okay, and this for all V in H. Okay, then you have to prove that chi is 0 using this property. Okay, actually you can work it. Those things I can actually explain. That's not the problem. It's actually enough to prove when you can assume without class optionality. You can assume that by taking an orthogonal complement, you can assume that H is one-dimensional. Then it is actually one-dimensional means C. One-dimensional means H. Gamma H will look like just direction C. C tensor, n times C tensor is again C only. Okay, so C tensor like that. So here instead of E of, you can take, you can assume that P of U, you can take it to be U to be 1, the number 1. For that you have to prove. For that he is using some Gaussian random variables and get the answer, which goes through some differential equation, second order differential equation, solution of that, many things, some Stirling formula. It seems to be quite difficult. I don't know. I searched the internet. I'm not able to see a simpler proof. I don't think anybody has considered this problem. This core problem, all those things. I don't think anybody considered this. Okay, so I am omitting that proof, but we will not use that fact that it is a core and all that. Okay, we will work on exponential domain and know that P of U, the domain of P of U is not exponential domain. It's much bigger. I can show that it's much bigger means I can show other, which are not in exponential. I can provide many vectors which are not in the exponential domain. Okay, which is in the domain. That is possible. I can provide that. All vectors are not determined. Okay, so we have to remember that. I will stop here. So I will prove the next statement in tomorrow's class. I will take class tomorrow.